Hi, I'm Eyal Cohen. I'm the CEO and co-founder of CogniFiber. It's a great pleasure to be here, and I thank the organizer for having us in DATE 2021. I hope you had good days here, and we are doing photonic computing, and it's a privilege to be among such distinguished colleagues. Of course, when such company is founded, we think about the future. We think about the future where AI is an essential part of the future, artificial intelligence, of course. We think about it at home, when we go to work, in our medical services, in the industry, everywhere, making our lives easier, safer, and better. However, if we want this kind of AI world to come into existence, we need to overcome a few serious obstacles. First, there is the exponential data that is accumulating, the heavy computing that is required by AI systems, limited electronics, because Moore's law is almost gone. It's hard to scale up electronics in speed and power consumption. If we talk about moving computation from data center to the edge, which is very important for real-time applications, then we need to consider the limitation of the edge in power consumption, in space, in heat dissipation. We cannot have a car with a 10 kilowatt computer, half a ton system, which requires a cooling system that drains a car of energy. So we need to think about new solutions to compute. And of course, in data centers, we need to find ways to reduce the latency, to have better computing with low power consumption, and of course, lower the heat dissipation for ecological reasons. So in CogniFiber, we believe in photonics, of course. We believe that photonic systems could reach up to 1 million times faster than existing systems. We believe that photonics will reduce the power consumption by at least 100-fold, and will be cheaper because it will replace hundreds, if not thousands, of systems existing today. And of course, almost no heat dissipation. So all the solution to all the problems at once, and if we can do it, it's of course a jackpot for us, for the world of AI. Of course, it's a great pleasure to do a photonic computing, because then you have experts from a cross-section, a multidisciplinary team with huge amount of knowledge and experience. We have experts in AI, in photonics, optics, software, hardware, and it's great to be among such a team with more than 50 years of accumulated years of experience in academic life, and more than 60 years of experience in startups and high-tech industry, both in AI, software, hardware, and photonics. So we are always welcoming great people to our team, and we're having a great time to develop new systems. So if we look at today's platform, what do we have? Of course, we have a regular CPU-based and GPU-based platform, which now dominate the AI hardware. Coming up are FPGA-based and ASIC-based. Most of the new startups are ASIC-based, and of course, this will accelerate existing systems, probably by somewhere between 5-fold to 10-fold, decreasing power consumption probably by several tens of percents, like 20%, 50%, etc. But this is not enough to bring the AI world. What we need is a Quizac-Haderach. We need exponential solution. So we can use photonics, for example, silicon photonics and photonic integrated circuits. Two of these means will be great in the future. Today, we have some interface problem with signal integrity issues, but I think there will be important parts in the future. We are talking about, a lot of talks are on quantum computing, big buzz, of course, in the papers and investments, but we believe that quantum computing will reach maturity probably in 5 to 10 years. So it's not feasible to talk about the coming solution in the 2-3 years to come. And what we suggest is a totally different approach of in-fiber photonic computing, where we use fiber materials to use devices where light likes to come and interface issues are non-existent. So what do we need of such a system? We need a good light carrier. We need excellent interface, fast and scalable. We need the material or the processors to be able to do modulation, both linear and nonlinear modulation with low energy, of course. We need the devices to scale. We need smaller devices or large devices to easy to scale them up. We want the system to be scalable, and this is very important. But it means that if we have generated a small system and we want to scale it up to a large system, we don't need to redesign the whole system. We just add many small systems, connect them together just through relearning or retraining of the system, and we have a large system. That is a scaled system, and this solution is yet to come. We need the system to be robust to noise, of course, and of course, we want to lower the risk and use as much as possible off-the-shelf materials and components. So this is what we are going for. So today, if we look at AI systems in a very grosso modo sketch, we can assume we have some memory operation, we have the interface, as I said, we have buffering and many types of computing, but one of the major computing is the multiply accumulate or MAC. And for now, let's assume the MAC takes around 95%. This is a lot, just to illustrate. And now we want to replace this MAC operation only with a photonic solution. And we will go from a MAC operation, electronic MAC operation to photonic. This will save, for example, 95% of the cycle of compute. However, this saves the time. It only gives us 20x acceleration. And it's not enough for the next generation. It will be enough for 1 year or 2 years, but it's not enough to have the AI world. What we want is to use the full bandwidth of light. And to do that, we need to implement the whole system by light. If we could, we have all the way from the inputs all the way to the outputs, everything photonic. But for now, we're trying to keep only the interface electro-optic and all the rest of the computing to do in photonics. If we do that, we're using a feed-forward neural network, all photonic, then we get additional acceleration of 5,000-fold, and altogether an acceleration that can go up to 100,000-fold. This is a huge, and this is now utilizing, far better utilizing the bandwidth of light. And that's what we aim for in CogniFiber. So as I said, CogniFiber aspires to solutions that have advantage in system bandwidth and scalability. So we want the system both to utilize the bandwidth of light in the system level, not in the chip level, but also to be able to build larger and larger systems by using combined smaller systems. So if we start with small system, it will be easy to scale up to larger systems. And neural network is about scalability. So the company is young. We were founded about 3 years ago. We have 5 patents, 8 employees, first world fiber-based processor, and already 2 LOIs with 2 great design partners, Applied ML and MagicFlex. Both of them have already contracts with international partners. Some of them are S&P 500 companies. So we have an opening to great markets in the Industrial IoT. This is Applied ML. And also in data center, this is MagicFlex. Applied ML applies safety solution using AI, while MagicFlex monitors devices in data center and optimizes the data flow. So both of these companies will serve as our door to the world, and we, with our photonic system, will be able to scale their profits between 10-fold and 100-fold. So this is a great win-win situation. What about our first processor? This is a very simple processor with 7 inputs, 7 outputs. All the inputs and outputs are regular single-mode fibers with standard connectors. That's why it's very scalable. So we can have 1 processor, 3 processors, 10 processors, or 50 processors, all manufactured easily, connected to one another via simple fiber connectors. That's the main principle. Additionally, because it's a fiber-based processor, its XY cut or area is about 300, 400 micron, the diameter. So we can actually pack up to 600 of them in a very small volume of 1 by 1 by 15 centimeters. You can imagine a box, a server box, that contains hundreds of these simple processors connected together in the form of a neural network, and all the outputs and inputs are all fiber optics. This is the revolution of fiber-based processors. So this processor, we showed that they are capable of implementing a neuronal function. That means we have the input multiplied by weights. We accumulate integrate these amplitudes. We have the MAC operation, and then it goes through optical amplification, where we implement the bias, and the nonlinear function, that is the ReLU or a sigmoid function. So we have the basic function of neuronal computation. And now it's only a matter of manufacturing tens of these units, combining them together into a network and training them. Of course, during training, we use a FPGA-based board to compute the error and correct the weights. But in inference, of course, all the parameters are fixed, and then we can have a system that works really quick. The only limit to the system is the input limit set by the transceivers. So the transceivers are the input and output of the system. So this is a really nice solution, scalable, easy to manufacture and achieve. Of course, we can build very small networks to do anomaly detection, like autoencoders. We can also build very large-scale networks for computer vision. And in our POC, what we did, we took the statistic of this touch unit, and we embedded this unit in a simulation, scaled it thousands of times, connected everything together, built a full network out of these components with their real-life statistics. And we built two networks, one ResNet 18 and one ResNet 50. And we ran standard benchmark with these simulations. It was ImageNet and Kitty. ImageNet is known for image recognition, and Kitty is for autonomous vehicles. And what we showed is this large-scale simulation of our unit can accelerate the inference 11,000-fold, while at the same time reducing power consumption by up to 70-fold with comparable result. And when I say comparable result, I mean 95% for top 1 result and 98 to 99% compared to NVIDIA in top 5 result. So this was a great result, and we now are ready to go on and build our first real photonic network in a system level. I didn't mention, but we compared this result to 10 cards of NVIDIA Titan RTX. So the comparison would be on the same scale. A single CogniFiber system versus 10 cards of Titan RTX of NVIDIA. What's next? Next, we want to generate much more complex processors with thousands of parameters that are inside each processor, not just 7 inputs, 7 outputs. And they could be scaled up to 100,000 of parameters per processor, a full neural network within a fiber. How do we do it? So we take a multi-core fiber. This is a standard multi-core fiber where we have several channels. Each channel is separate from each other. The cores fiber cores are far away from each other, and there is no crosstalk. So the same data introduced to one channel is the same data that goes out. This is, of course, what is used in telecommunication, optical communication today. And there are 12 cores, 19 cores, and more in the industry used. But what we do is very different. We take the cores and we allow some of them to be very close to each other. Thus, we create crosstalk intentionally, but it's not just crosstalk noise. We use this crosstalk as a compute. How? In the same way that in a transistor, the gate controls exactly what is the current between the source and the drain. In the same way, we can control with one core, we can control the flow of light between two other cores, like a gate, a source, and a drain. How do we do that? First, by, of course, setting the distances. So, of course, very close cores are influencing each other and will have the crosstalk, but further away cores will not. So the design is first setting the borders of which cores can crosstalk to which. But it's not only that. We control it dynamically by amplifying each core separately. Amplifying the same way as done in fiber lasers and LEDs, using just a second wavelength as energy source and amplifying the signal. So we amplify each core separately, and by using amplification, we can do several things. First, we can do mathematical implementation either linear, like the weights, or non-linear, like ReLU and sigmoid. But we also control the amount of light that is flowing from one area in the fiber to other areas. So also light flow control, but also mathematical implementation. So what you can imagine is we can introduce a full network into a fiber in this way. Assume we have many cores and they are arranged in a way that are resembling a neural network. Here in this case, we have inputs on the outside, and the outputs are on the inside of this network. And when the light passes through the fiber, you see, it goes from the external core, the input cores, to the next layer by the same principle I showed you previous. These cores are close by, then they're crosstalk. This crosstalk leads to the propagation of light from the external core to the medial cores. Again, this done again and again. What happens during the passing of the light through the fiber, it actually scans the whole network, and you have to remember that each core is amplified differently. If there is no amplification light, it will quench the light. It will cause a negative gain. If the medium gain, it will have maybe zero gain or low gain. If we have a lot of amplification, it will have a positive gain. And it could also implement, as I said, a nonlinear function. So each element in this network is either a synapse or a neuron body or an axon, and together they implement the full neuronal function with many layers, as many as possible. These types of fiber we can reach today in polymers up to 10,000 cores per fiber. So this is a huge amount of cores we can use. In the future, we plan to have a photonic rack in a data center. That means that we have a rack-sized machine, which inside this machine will have 1,800 processors, not 5, not 10, not 100, 1,800 processors sitting side by side. You see this hive-like structure. Each one of these processors is this hexagon, 3D hexagon, about 3 centimeters wide and about 10 centimeters in length. And this hexagon has 6 ports. Each port have at least 1,000 cores inside that are transmitting optical data in maximal speed of optical communication. And that can lead up to 1 petabit per second per port. Okay, 1 petabit per port can be input or output from this processor, and each processor talks to the 6 processors that are on his side. So light can propagate from one processor to the neighboring processor, etc., across all these processors. And each area within this processor field could use to implement specific neural network, a full neural network, or layers within a specific very large neural network. We have here an unfathomable amount of processing power, where each processor, the interconnect, is in the speed of total 6 petabits per second, and each processor implements a full neural network with at least 10,000 flops, without 10,000 flops. But if you multiply by the rate of the input, you get thousands of petaflops per processor. So you can imagine the power of computing of this beast. Now, of course, this is not a standalone beast. We need an input rack to take all the input from the outside world, all the data incoming, of course, in super fast fibers, optical communication, 200, 400 gigabit per second, tens of them or even hundreds of them, and get this data into the system, into the photonic racks that can talk to each other via fiber as well. And we have an output rack where the output of the system is then modulated into regular pulses for the optical communication clients. And this is going to replace very large areas in data center, and on the one side, produce great acceleration, even 1,000,000 times acceleration of existing systems, and of course will reduce power consumption dramatically and heat dissipation. This is the future that we envision in CogniFiber. I thank you for the time, and I'm expecting your very interesting question. Thank you.